Hello and welcome back. This video will start section 3.2, which is looking at variation in data values, essentially the spread of the data. In the previous section, we looked at the center of the data, which if you're given, say, like a normal bell curve, some sort of distribution, we can typically identify the center. But then even if two distributions have the same center, they may be more or less spread out from one another. So we will say that when we have sort of a wider distribution or a wider set of data values, we'll say that this has more variation. More variation. So in order to get a numerical value for this, there's a couple of options. The first one is not necessarily very good, and it's simply taking the range. We just take the maximum data value and we'll subtract the minimum data value. This is not resistant to outliers, so if we happen to have one data value that's unlike all the rest of them, say it's really, really big, our range is also going to be very big. So it doesn't really do a good job of describing the variation in the data. We could have 100 values that are all the same and one value that happens to be a lot smaller. The range will be pretty big, even though most of the data values are the same, so there shouldn't be very big variation. So we're essentially going to focus on the standard deviation in this chapter, or in this section. And with the standard deviation, again, it's a measure of how the data values sort of vary, but in particular we're looking at how they deviate away from the mean. So essentially this gives you some idea of how far away are the data values from the mean. So we'll use an S, a lowercase s, for the sample standard deviation. So if you're given a sample of data, we'll use S for the sample standard deviation, but we'll use a lowercase sigma to represent the population standard deviation. So quite often we will use S to try to estimate sigma. We can calculate S from a sample so that we can try to guess or estimate what the entire population standard deviation is. And just a little bit of notation from last time, we use X to represent an individual data value, X bar to mean the sample mean, and N to mean the sample size, so the number of elements in our sample. Now, I'll only introduce the formula for S in this video, and we'll talk about sigma in the next. So here's the formula. There are in fact two formulas, and they are equivalent. They mean exactly the same thing. They're just written in slightly different ways. So the first formula is fairly complicated. We're going to take the square root of this big thing. And when we look inside of this, I want to point out that the main ingredient here is we're going to be taking x minus x bar. This right here is we're going to take each data value and we're going to see how far away it is from the mean. When we take x minus x bar, what we're doing is we're looking at the distance from a data value to the mean. And once we know how far away things are from the mean, we can use that to get a measure of how far the entire data set, how spread apart the entire data set is. So we'll take these values, we will square them, raise them to the second power, we will add them all up, divide by n minus 1, and take the square root. This is quite a few steps, so we'll go through an example in just a second. This second formula is fairly similar. I see I have a mistake here. The idea is that we want to take the square root of, so again, n times the sum of all the data values squared minus the sum of all the data values squared. Notice that here the squared is on the outside of the parentheses rather than on the inside. And we'll divide by n times n minus 1 before we take the square root. This formula is a little bit harder to compute by hand, but it's usually the formula that calculators and computers will use. We will focus on this top formula. It's simpler to calculate. So let's go through an example and we'll use this formula. So we want to find the standard deviation of the following data set. It's just the first 5 numbers, 1, 2, 3, 4, 5. So what do we need in our formula? Well, we're going to need all of the data values x. Well, there they all are. We don't have to do anything more. We also need x bar. So x bar is going to be the mean of the data set. And again, the mean will take the sum of all the data values, 1 plus 2 plus 3 plus 4 plus 5, and we'll divide by the number of data values that we have, which also happen to be 5. We've got 5 numbers. So this is 15 divided by 5. So the mean of this data set is 3, which makes sense. 3 is about the middle of this data set. Also, n, we already mentioned, is just the size of the data set, which is 5. So we now know all of the ingredients to calculate this. So the first order of business, I want to find x minus x bar. And the easiest way to do this will be to create a little chart. So we'll have all the values for x, 1, 2, 3, 4, and 5. And then we will look at all of the values that are x minus x bar. So remember, x bar is 3. So 1 minus 3 is negative 2. 2 minus 3 is negative 1. 3 minus 3 is 0. 4 minus 3 is 1. 5 minus 3 is 2. Next, we want to look at this quantity squared. Because again, in our formula, we have x minus x bar quantity squared. So we'll just square all these numbers. Negative 2 times negative 2 is 4. The negative signs cancel out. Negative 1 times negative 1 is 1. 0 times 0. 1 times 1. And 2 times 2. We have all of these data values squared. Okay. Next, I have to plug it into this formula. So on the top of this fraction, I have the sum of all of these squares. So let's do that. Let's take the sum of each one of these squared numbers. So 4 plus 1 plus 0 plus 1 plus 4 happens to be 10. Okay, that was easy. Next, that's the top part of the fraction. The bottom part of the fraction is just going to be n minus 1. N is 5, so n minus 1 will be 4. So I need to find this fraction. The sum of x minus x bars squared divided by n minus 1 is the same thing as 10 divided by 4. 10 divided by 4 is about 2.5. In fact, it's exactly equal to 2.5. The last part, we need to take the square root of this whole thing. So the square root of the sum of these differences squared, all divided by n minus 1, is the square root of 2.5, which is approximately 1.6. Now, I have rounded to one place after the decimal because each of my data values, I'll draw this in a box here, each of my data values, this extends 1 past the rounding here. So each of my data values is a whole number, so I'll go 1 past that to 1 decimal place. And this is our standard deviation. So 1.6, which I'll explain in a little bit more of in the next video, will describe how spread apart these data values are. So before we talk about what these numbers actually mean, as we calculate this, we should keep a couple properties in mind. First of all, S is never negative. It describes the spread of the data, so we don't want a negative spread here. And the only time that S would ever be 0, essentially the spread would ever be 0, is if every data value is exactly the same. So there is no spread to the data. And in particular, when we see larger S, that means there's a larger variation in the data values. So the data is going to be spread out more. Smaller S means the data values are going to be closer together. One thing, S is not, so the standard deviation is not resistant. So if there are outliers, it can make S pretty big. So again, one way to see this, if there are outliers, the data is more spread apart, which means S will be larger. The units of S are going to be the same as the units of the data values. And a good way to see this is with an example. If we were looking at variation in heights of humans, so we might measure height in inches, let's say, the spread of the data will also be measured in inches. So the units of standard deviation is measured in the same with the same units as the data values. And then lastly, one thing that's important to mention is that S is a biased estimator of sigma. So S is the sample standard deviation. Sigma, lowercase sigma, is the population standard deviation. And usually we'll take a sample to try to estimate sigma. One way to try to estimate it, maybe we take a bunch of samples, we calculate all of their S's, and then we try to estimate what sigma will be. It turns out that these S's won't be spread around sigma, but they'll normally be either all higher or all lower than sigma itself. So it's not the best estimator, but as long as we know that it's biased, we can use this in our calculations. So I do want to go through just one more quick example of finding the standard deviation. And what I'll do is I'll change the previous example just a little bit. I'll add a couple of 3's in here. So now we have 7 data values. So again, we need to calculate the mean. This is always the first step. So 1 plus 2 plus 3 plus 3 plus 3 plus 4 plus 5 divided by the number of numbers, which is 7. So this is 21 divided by 7, which is 3. So the mean hasn't changed. The center of the data, the mean, hasn't changed. As in, both of our data sets have the same mean, but now we have more data values, and they're clustered around 3 a little bit more. So we might expect the spread, the standard deviation, to shrink just a little bit. So let's calculate our standard deviation. We'll need to look at all the values of x, which are 1, 2, 3, 3, 3, 4, and 5. We subtract the mean from x. So 1 minus 3 is negative 2. 2 minus 3 is negative 1. 3 minus 3 is 0. 3 minus 3 is 0. 3 minus 3 is 0. 4 minus 3 is 1. 2 minus 3 is 5. We take each of these values and square them. Essentially, this makes all these numbers positive because we want a positive spread. So negative 2 times negative 2 is 4. Negative 1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. And again, we go through the same steps. We want to add all of these squares. 4 plus 1 plus 0 plus 1 plus 4. That's still 10. And we want to take this sum and divide it by n minus 1. So n here is 7, so n minus 1 is 6. So this will be about 1.6 repeating. I will keep this number exact for the moment. I won't round it until the very end. This is always important. And now I'll take the square root. So this is the square root of 1.6 repeating. And this is approximately 1.3. So again, the spread before was 1.6. Now the spread is only 1.3. Even though the mean stayed the same, our data values are clustered a little bit more around the center, and they are not sort of as spread apart.